Reshef.
Thanks, David. This is a joint work with Yair Zik from Nanyang in Singapore, and Edith Elkind, which used to be Yair's advisor, and Jeff Rosenshine, which was my advisor during my PhD. And I'll talk about several issues together. I'll try to bring them under one framework. Okay. So first thing, just to get an idea, so how many of you know or heard of cooperative games and the core? Things that? Okay. How many know the tree width of graphs, tree decompositions and tree width? Okay, so it's not critical actually. So the first topic is actually quite fundamental for the talk, but fortunately it's quite easy to explain. So we'll spend the first few minutes as an introduction to cooperative games. And the second one is a bit more technical, but it's not very crucial to understand the talk. So even if you've never heard of the tree width, it shouldn't be a problem to follow almost everything I say. Okay, so we'll start with cooperative games. Okay, so cooperative games are general. They've been introduced kind of around the same time that non-cooperative or standard game theory was introduced. But in cooperative games, we don't really care. We don't model the actions that the various agents can do. The only thing we care about is how groups form and how they divide profits that arise from cooperation. So we don't say this agent does that and that's how the value is created. So we assume that every group has an ability to create some value. So maybe this group can somehow together generate $5, and this group can generate $3, and the value has to be defined for every possible group. Okay, and then somehow the society divides into groups and that are mutually disjoint, and every group creates or generates its own value, and then they somehow need to share this value. Okay, so now these three agents somehow need to decide, maybe sign an agreement saying how they share these $5. Okay, and more or less all of 90% of cooperative game theory is about how should profits be divided. Okay, and the other 10% is maybe on how agents form these coalitions. But suppose that they just form the optimal partition. Right? Okay, so just a little bit of notation. So we usually denote the agents by n. We have n agents. And every coalition we denote by S. And the game is a very simple construct. It's simply defined by this function that gives a value to every possible coalition. This is a game. Okay? This is how a game is defined, a cooperative game. Okay, okay, then we have some simple classes of games. We say that a game is TU stands for transferable utility, because we can also think of situations where not all value allocations are possible, but here we have no constraints, and if some group generates $5, then they can somehow divide these $5 any way they want. Okay. And the game is simple if the value is always 1 or 0, so coalition can be either winning or losing. And there are also other classes, but it will be less important. Okay, so like we said, the value can be distributed in any way. So what is an outcome or a solution of a game? First, a partition, but we just assume that they somehow form the optimal partition, or they all group together for one group. And then we need to just say exactly, there's a vector, say how much exactly each agent gets, which is just a division of the total value. Okay, so it needs to sum up. Yeah, this is sum over xi. It needs to sum up the value of every coalition that is being formed is exactly divided among the agents that are forming this coalition. Okay, and if there's more than one coalition, then they cannot transfer value from one coalition to another. So every coalition has to somehow divide its own values within its members. Okay, so a solution is just a partition, and for every coalition, a division of the value. Okay, so not every outcome is good. We have several requirements. First of all, it doesn't make sense if someone gets less than what he or she can make on their own. right? So if my the coalition of myself makes $10, and now someone tells me, okay, come join my coalition, I'll give you $5, then it doesn't make sense. Okay, I wouldn't join. It would not be stable. So that's like a very minimal requirement. Okay? And we can now extend this requirement to more general requirement, saying that not just every single agent has to be like satisfied from participating in a coalition. This has to be the case for every set. So suppose that I know me and David together we make $10, and now we join a coalition. And in this coalition, say I get 3 and David get 2, then together now we get less than what we can make on our own, right? We can just move aside and form our own coalition and generate 10, which is more than 5, which is what we get together, and then split the 10 in a way that is better for both of us. Okay? And if we generalize this requirement, we want every coalition to get it. So this just stands for the sum of payments in the coalition. Okay, X of S is additive. It's just the sum of payments to a member of the coalition. It has to be at least the value of the coalition. Because otherwise, this coalition S will just deviate from the agreement. Okay? It doesn't make sense for them to sign such an agreement. Okay? So all vectors S that have this property are called the core of the game. And this is the most fundamental concept in cooperative game theory. Okay, so I guess most of you are computer scientists, right? So these are just, you can notice that these are just linear constraints. So if we have variables that are x1 to xn, we have n variables, and we want to set values, we have a set of linear constraints on their sums. We have quite a lot of them, actually. So we have an exponential number of constraints, but these are linear constraints. And the core is just the solution, or all the solutions of this linear feasibility program. Okay. Okay. Unfortunately, some linear feasibility programs might not have a solution. Okay. Maybe these constraints are somehow contradicting, and we can see one such example. A very simple example. It's called the ice cream game. So imagine there are 3 kids, and they have, so an scoop of ice cream costs, say, I don't know, $2, and they each have $1, and so 2 of them can buy a scoop, or 3 of them. If 3 of them together can also buy a scoop. But then they need to decide how to divide, so the value here is in value in ice cream, not in dollars, okay? So they need to decide how to divide the ice cream. And let's see how, like, what can they do? Okay, so suppose that the 2 of them buy the ice cream and they share it in some way, say half-half or 2/3 third. And now we have another. The 3rd kid didn't get anything, right? So he can come to one of them, say to the one who got less. So we have one who got 3rd and one who got 0, and together they can split off and buy a scoop together. The scoop equals 1. It's more than 1/3, which is what they currently get. Okay, so this allocation will not be stable. And in fact, in any allocation of the ice cream, we will have 2 kids who together get less than a scoop, right? And these kids will not sign this agreement. Okay, is this clear? This example clear? Okay, so even if in a very simple game, the core might be empty. Okay. Now, last week, Jasper here gave a fantastic talk. And one reason that it was so impressive, I think, is that he gave one solution or one framework that can be applied to a lot of real-world problems. Now, I'm a theorist. I used to work on this problem and other problems. And I consider a problem interesting. You know, if smart people worked on this model, suggested it, and proved interesting things about it, then maybe it's interesting from a theoretical point of view. But then after last week, I thought, I mean, we didn't find cure for cancer or made cheetah robots run or anything like that. But maybe people have tried to apply these cooperative games to actual problems in the real world. So I went checking, and apparently people have tried to do various things. So this is one interesting paper where they looked on actual agreements that companies, like power companies, I think in the Tennessee Valley, signed in the 30s of the 20th century, and they compared how does this comply or does not comply with various cooperative game theory concepts. And then there's been a lot of other work where people try to actually take a real problem, and then use concepts like the core and variations of the core to generate better agreements and see if it really works in various places and various topics. And one topic that particularly got a lot of attention is water management. There have been a lot of papers on applying cooperative solution concepts there, but not all of these applications were successful. In fact, some of these papers are rather critical, and they're comparing this to other methods, and they show that some of the cooperative concepts can't really work. And at least these are not the only reasons, but two reasons that these authors highlight when they talk about a particular application in water management is that they actually say that the core may be useless, or when they tried to apply it, they found it was useless because of two things. One, that it was difficult to calculate or difficult to compute payments in the core. And the second is that it was empty. So I will not talk about this problem. First of all, what was difficult to compute in '92 is much easier to compute in 2013. And there have been a lot of work on computational aspects and complexity aspects of the core and other solution concepts. So I will not talk about that. But this seems a more fundamental problem. Okay? Because, okay, if it's difficult, maybe, I don't know, buy another computer, use more efficient algorithm, you can somehow go around that. But if the core is empty, and we saw that it can be empty even in very simple cases, then what can you do? Okay? And this is what I'm going to talk about. Okay. So one thing that we can do is first understand why is it empty. Okay? One interpretation of why the core is empty, we can think about it as there's just not enough value to satisfy everyone. Okay? We're trying to divide a cake. Right? So now we turned from ice cream to a cake, but it's the same thing. There's a theme going on here. And there's simply not enough cake for everyone. So any way we divide it, some agents are not happy or unsatisfied. Okay? So one way to go around that is have more cake. Okay? So suppose that there's some external entity, I don't know, the government comes and say, okay, so if you cooperate, I'll give you more cake or more value. Okay? But this is conditioned on the fact that everybody cooperates. So this enlarges the cake. Now we have a better cake, or a bigger cake. And this bigger cake, we can divide it in a way that satisfies everyone. Okay? The concept of subsidy is, of course, not new. But it turns out that in this case, it can be applied in various manners. Formally, what we did is we created a new game. Okay, we changed we changed just one constraint. Actually, we only changed a constraint on the sum of the payments. Okay, so all the feasibility constraints are still the same. Every coalition should get at least what it can make on its own. But now the constraint on the sum is not just this, but it is this. Okay, we enlarge the cake. So in a previous paper, we have studied this. And this is a work that I was also involved in. We studied this subsidy notion or cost of stability notion in a systematic way. So first of all, this is a simple observation. If we add enough cakes or enough value, then we can stabilize any game. Okay, one trivial way to do it is just multiply the cake n times. Okay, so why would that work? Because then we can just give anyone a whole cake. Okay, so that must work. if we do this, then every coalition gets at least what it can, because no coalition can make more than a whole cake. Okay, than the value of the optimal coalition structure in that case. Okay, is that clear? Why this must hold? Okay, so if we're really willing to subsidize with an unlimited amount, then it's not a problem. But of course, especially if someone is subsidizing you, then it's the government, they don't have unlimited amount of money, and they want to minimize the subsidy, but still achieve cooperation. Okay, so the cost of stability, it was defined in this paper as the minimal subsidy that is enough to stabilize the game. Okay, or if you want to present it more formally, by how much we need to multiply the value of the game, the optimal coalition structure, in order to get a non-empty core. Okay, and so this direction got a lot of attention. Actually, it was, I think it still is the most highly cited paper that came out of SAGT, this conference. It's still not like a huge conference, but it attracted a lot of attention, both in computational aspects, and people looked on various classes of games and tried to compute or give bounds on the cost of stability in these games. Yeah.
Do we know what happens if the core is empty?
Yeah.
Is there any way to say what would happen if like players play a non-cooperative game or some? Is there any way to say, like, to compare this to what happens if you don't use the subsidy?
I don't quite understand the question.
What's going to happen? Is everyone going
Oh, you mean, okay, so there are other solution concepts. Okay, the core is not the only solution concept. There are other solution concepts. One of them, or one that is, there are variations of the core which are never empty, which basically look on what happens. So we now assume that the coalitions will relax their demand until finally we'll find something that is stable enough. This turns out to be very close to this solution concept, to the cost of stability. And maybe I'll say something about that in the end. Okay, but there are other solution concepts. But people like this solution concept because it's very strong, right? It says that no coalition can deviate at all. It doesn't matter what you assume on their behavior. Okay? Yeah.
So I'm trying to think, so how do you imagine the coalition structure is chosen, and who chooses it? The same entity that's deciding the subsidy, or?
Okay, so first of all, there's a lot of literature on coalition formation. And mainly, I think most of it is about finding either centralized or decentralized algorithms to find this optimal coalition structure. Now, conveniently, it turns out that the optimal coalition structure is also the one that is easiest to stabilize. Okay, it's the one that requires the lowest amount of subsidy.
I guess what I'm wondering is, if you imagine that, sorry, so if the coalition structure is centralized, is decided centrally, then people don't really have an option of defecting and saying we don't like this coalition structure because it's enforced centrally.
Okay, so the Okay, so I think I'm getting what you mean, and I think that if the government says something like this, okay, if you sign an agreement that if everybody agreed to sign whatever you want, but if everybody agreed to sign, then instead of $100, then then you'll get a subsidy of $50, okay, or whatever. You'll get a subsidy of 50%. I think that should be enough. The center does not have to force a particular agreement because of what I said, because the optimal structure is also the one that requires the least amount of subsidy. So maybe there are others, maybe they give subsidy that is too high, and then it will allow other coalition structures to form too. But so what? So suppose that the center is only interested in stability, not in the actual outcome.
If you imagine the value that the coalitions are getting is partly coming from a source other than the government. That's the original game, and then there's the subsidy on top of that, which is coming
Yeah, it's external. It's something external.
If it's all coming from the government, then there's
Yeah,
not really an option
of course. Yeah, but subsidy. But in many cases, you know, the government subsidizes the company because the company can generate some profit outside, right? You subsidize your export and so on. And there's actually some work on internal subsidy where this subsidy is not really external, but then it has to be distributed again as tax. So there's some taxation, and then you can give this taxation as a subsidy. But we didn't look into that. Okay. If you're interested, there are papers on that. Yeah.
Is there something nice about welfare here? You kind of alluded to it. So if the optimal coalitional structure is the one that's easiest to subsidize and is also welfare maximizing somehow, then
Yeah.
if the government gets it right, then and people play to something that is actually stable, then you can select for an optimal structure.
So the optimal structure, like by definition, is the one that generates the most value. That maximizes the social welfare. So that's by definition. So I don't understand what you need to select here.
So then that's right. So there's some magic number where at that number the optimal coalition will be stable and no other coalition will be stable.
Yeah. If the core is non-empty. Yeah. Yeah.
Assume that the extra is infinite, that the player has an infinite resource.
Wait, you mean the subsidizer, the government? So
Infinite resource.
yeah, so like I showed, there is some limit, so he never needs to pay more than n times the value of the game, and he tries to minimize that. So we'll see what's the minimum that he can pay. If he doesn't even have this minimum, then we can't apply the subsidy. But for now, yeah, assume that the government has unlimited resources, but it is not willing to spend them. So it wants to spend as little as possible and still achieve cooperation. Okay, maybe we'll show an example, and I hope it will be clear after that. Okay, but if you still have questions, then of course. Okay, so we'll go back to the ice cream game. Okay, and here instead of the government, we'll have, I don't know, maybe mommy that is willing to buy them more scoops if they, if they behave nice and cooperate. So initially they could only get one scoop, but now suppose that we tell them, okay, but if you all buy ice cream together, we'll add half a scoop on top of what you can buy yourself. Okay, so now they have 1.5 scoops, and 1.5 scoops they can actually partition in a stable way. So every child can take half a scoop, and this is stable because no pair of kids can generate more than that. Because if they split off, then they don't get the extra half. They can only buy one. Okay, and one is what they already have. Okay. Other questions about this? Okay, so this shows that the cost of stability of this particular game is at most 1.5, right? Because by multiplying the value by 1.5, we achieved a stable partition, stable allocation. Okay. And can we do anything better in this game? Can we achieve that with a subsidy of less than half? Yeah, so clearly we can't, right? Because if we give less than half, then we'll still have a pair that together make less than 1, strictly less than 1. Right? Anyway, we divide the say, I don't know, 1/3 scoops. Okay, so this is tight for this particular game. So the cost of stability of this game is exactly 1.5. Okay. And what we did actually, if we look on the general case, we moved from a linear feasibility program to a linear optimization problem. Okay, we're trying to minimize the subsidy such that all the other constraints hold. Okay. Any other questions? Yeah.
$1 and a single scoop was $2, right? So if you subsidize subsidize in this way, how much do the kids actually pay? Or do we not care about
Yeah, this dollar might be confusing, okay? So just think about it as every 2 kids or more can, they can buy a scoop. They have enough resources, some abstract resources, they can buy a scoop, okay? And 3 kids together can also buy just 1 scoop. They can't buy 2 scoops or more.
So with the subsidy, what is the core? Is the core like, is the 3 kids cooperate?
Yeah, that's a good question. So that's a good question. So in this new game, the total value is 1.5, right? And this is the only payment that is in the core. Half, half, half is the unique payoff allocation that is in the core of the new game, okay?
So, okay,
And we call this,
the
yeah.
definition of this game, if you split up into 2 and 1, with the subsidy, you can't have like the 2 kids getting 1 and
No,
the 1
no. Okay, so to be more accurate, so the core is having 1 group of all 3 agents, of all 3 kids, okay? They don't partition to 2 groups. They have 1 group. They split into 1 group, and this is how they share the payoff, okay? And we call this the extended core of the original game, G. Yeah. Well,
Sorry, so I think of 2 ways to formalize this. One would be I create a new game, and I say you're now playing this game.
Yeah.
The other would be like you're playing the old game, and if something happens, I'll give you a point.
yeah, but that will be equivalent.
Okay, there's no difference.
Yeah, it's easier, like mathematically it's easier to think about it as a new game, okay, where we changed the constraint. But if you look at it as an optimization problem, so every single game is a feasibility program, okay? And if you look for so you have like a continuum of games, right? Because you can add all kinds of subsidies. And if you look at you're looking for the game where this exactly happens, then you actually get a linear optimization problem, okay? Okay, so I promised you social networks, and so far we haven't seen any network, right? So we'll correct that. So we have an exponential number of constraints, or we kind of assume that every coalition can be formed, or that every coalition can somehow recognize that it has a higher value and then deviate. Okay, but that might not be the case in a lot of practical situations, because coalitions may fail to realize that, or they may even not know one another enough. So in a model that was introduced by Myerson, 1977, he assumed that agents are forming some sort of social network. And what is a link? So the links are social links, and we can interpret them in various ways. One way we can think of this as a communication link. So these 2 agents can talk. And another thing we can think about this is friendship or trust links. But the important thing.
The numbers are just indexes, right?
Yeah. This is just the name. These are the names of the. Yeah, I'm sorry. These are like the names of the agents. Okay, they have no meaning. Okay, and this means that not every coalition can be formed. Only coalitions that are connected in this graph can be formed. So I'll give an example. Okay, so this coalition can be formed, okay, because all of its members can communicate, or we can say that all of its members know one another either directly or indirectly, but they do not need other agents in order to communicate. Okay, they can sign whatever agreement they want without using anyone from outside. This coalition is not allowed now because 7 and 3, they have no way to communicate only by going through agents inside the coalition. They have to use someone from outside. So you can think about it, if they want to sign like a side agreement, they have to use someone from outside. But why would someone from outside help them in their scheme? Okay. So this is a very natural model, I think. It became quite popular. So how does it affect the cooperation or the cost of stability? So let's see what is known or what can be inferred easily. So first of all, I showed you first that the subsidy is never more than n, but in fact, this can be reduced to square root of n. Okay, this is some of our previous work shows that. I will not show you exactly how, but you never need more than square root of n. Okay, in any game. Okay, regardless of the structure. Oh, why did I draw here a click? Okay, because if we have a click, then we're back in the original case, right? If we have a click, then every coalition can communicate and every coalition can form. Okay, so a click in the Myerson model is just a regular game, standard game. The other extreme case is that when we have no edges, and here no coalition can form. The only thing that can form are singletons. And then we can just say, so everybody can take what he or she make on their own, right? And this will be stable, right? So if we have no edges, then this is trivial. The core is non-empty. Okay. And it turns out that we can even go a bit beyond like the empty graph, which is not very interesting, to trees. So this result was shown several times by different researchers. So it's known after Demanje, but she was actually not the first to prove this. I think Ricky Vore once said, it doesn't matter who proved it first, it matters who proved it last. So she proved it last. It's a very simple argument showing that if the structure is a tree, then any game has a non-empty core. So you don't need a subsidy if this graph is a tree. And there's also a very easy, constructive way to find a core allocation. Okay. So we have like these two extreme cases, tree and a click. Yeah.
In that case, does the subsidy need to be higher?
So here you don't need a subsidy at all. So here you don't need a subsidy at all. If it's a tree, this means that you don't need a subsidy. Okay, and G like underscore H is like the game G played on the graph H. Okay, so if this H is a tree, then regardless of what game you're playing, you don't need a subsidy at all. Yeah.
Is there any limitation on the valuation function?
No, that's the thing. Any game means any valuation function. Okay.
But you have no coalition, or not the broadest coalition.
You need to allow every coalition structure, and this means you can stabilize the optimal coalition structure with no payments. If you want to stabilize the grand coalition, then this holds for super additive games. Okay. Okay, so we have these two extremes, right? So we know what happens when we have a tree. Okay, we know what happens in the. So like this is tight in the worst case. So there are examples where you actually have to use square root of n. And I guess the main question is, what happens in all the other cases? So there's like most of the graphs are neither clicks nor trees. Okay, so we need to somehow say what happens about everything in the middle, or what is somehow to characterize the connection between the network structure and the cost of stability, or the stability of the game. Okay, this is our main question, and for this I will need to define one more thing. So if you have like any other questions on like this network structure or cooperative games, then now. Okay, great. Okay. So we want to say something about the structure of the graph. So we need to somehow quantify maybe the complexity of the graph. So it seems that like complex graphs, like clicks, they're hard to stabilize, and very simple graphs like trees are easy to stabilize. And we have all kinds of metrics to how complex a graph is. So some things are, we can look at the degree, we can look on expansion, we can look on connectivity. I guess people here, some work in networks, they know they can extend this list on and on. But we focused on a particular parameter of the graph, which is the tree width. Yeah. Yeah. Okay. So who can answer that? So suppose, there's a board here. So Yeah, no pen. Yeah. Um, yeah. Okay. So we have 3 kids, right? And this is a tree over the 3 kids. And here's a core allocation. So give everything to this agent, okay, to this kid. This kid gets the entire scoop, okay? Now, these 2 kids can't do anything about that because they can't form a coalition. They don't know one another, okay? That's a good question. I hope that makes things clearer. Yeah. It's good to be in the middle.
One of the rules of the game where the 2 or more keys together, not a single key.
All 3 participate, the middle one gets.
Yeah, they like sign an agreement. So this is a stable agreement. It's a group of the 3 buying a scoop together, but he gets all the ice cream. Okay, and there's actually one application of the Myerson model was for line graphs, which models some sort of a political setting where you think about you're sorting parties, say, I don't know, from most right wing to most left wing, and then you look for which coalitions will be formed, and the center players get like most power. Okay. Okay, so I will not give a formal definition of the tree width, but I will explain in just a few words. Okay, so you have any graph, and a tree decomposition is some structure, some tree structure over this graph where every edge is contained in at least one bucket, and every variable is connected. Okay, so if you didn't get that, it doesn't really matter. It's not critical. Okay. But notice that one way to achieve what I said is just squeeze everybody into one huge bucket. Not huge, it will be size n. One huge bucket is a valid tree decomposition, but it's not a good one. So how do we measure the quality of a tree decomposition? This is what we call the tree width. It is the size of the largest bucket minus 1. Okay, so the grand bucket will have a width of n minus 1, which is not so good. Okay, and this tree decomposition has a width of 2 because the largest bucket is of size 2. And if you don't want to think about any formal definitions, then just think about tree width as something that says how close this graph is to being a tree. So a tree has a tree width of 1, and only acyclic graphs have tree width 1, and cliques have tree width of n minus 1, and things in between have tree width in between. Okay? Okay, so of course we did not invent this notion of tree width. This has been studied for quite a long time now, and mainly in algorithms. So it is known that a lot of graph algorithms on problems that are generally hard, like hard on general graphs, become easy when the tree width of the graph is bounded. So this is just a partial list of like problems that suddenly become easy when the graph is has a bounded tree width. Bounded, I mean constant, because the complexity will still be exponential in the tree width, but if the tree width is small, then it is still polynomial in the size of the graph. So you can see why squeezing everything to a single node is not really helpful, because it will just be exponential in the size of the node, which is basically n. And we can see that there are also some game-related problems here, but still, this is about algorithms on games, how to compute various things. Okay. Okay, so now back to our original question. So this was our main question, right? We did not want to find anything efficient. I told you we're not worrying about computation. We were worried about the core being empty. Okay. So what is the connection now between the structure, or between the tree width, now that we're focusing on that, and the cost of stability? And now I can just bring you our main result, okay, which is a very clear connection. Okay, the tree width of the graph gives you a tight bound on the cost of stability. And this works for any game, okay? And any graph of, like, if you have a bound on the tree width of the graph, then you have a bound on the subsidy required to stabilize the game. Okay, yeah.
So in what sense is it
Okay, it's a good question. Okay, so here no asterisks are needed, but here there are some tweaks. So what do I mean by tight? So first of all, I showed you a square root of n bound, so it's actually the minimum between this and square root of n. Okay, and by tight I mean that for every number, okay, I can give you a graph and a game on this graph, okay, that matches this exactly. Okay, so maybe you have some graphs with high tree width where the subsidy is still bounded. Okay, so you can maybe do something more delicate there. But if everything you know is the tree width, then this is tight. Okay.
Can it be every value up to the square root of n, or?
Yeah. So it's tight for every value up to square root of n.
Sorry,
Yeah.
you saying something about trees as well?
Yeah. Okay. So it's a good question. So does this generalize the Mange result? Okay. This is a good question. And so suppose now we substitute it. So if h is a tree, then a tree width of a tree is 1. Okay. Then we get a bound of 2. Okay. So it seems that it does not directly generalize. So we have 1 for trees, or the tree width exactly for trees, and then the tree width plus 1 for everything that is not a tree. The tree width of a tree is 1. Okay? I can show you why. Because a tree decomposition of a tree itself has, you have to take every edge and stick it in one bucket, right? So the bucket will be of size 2. Okay.
You say this is tight when the tree width is...
Yeah, exactly. Yeah. But so the Mange's result does not follow exactly the special case from this, but in fact, the same technique also provides. If you do so, we prove it using the tree decomposition. But if you run the same proof on a tree, not on a tree decomposition, then you basically get the Mange's result. Okay. And then we were a bit baffled by this, and we thought we tried to shave off this +1 for a long time because I thought, okay, this must generalize, the result on trees somehow. It's kind of weird that it's 1 for tree width 1 and then tree width +1 for everything else. But eventually it turned out to be impossible. I'll show you just an example later. But so I will not show the proof. The proof of my unbiased opinion is that it's very nice and elegant, and you should look at the paper. But I tried to give you an intuition by showing a very simple case. Why hold in a very simple case? In this simple case, we'll make 2 assumptions on the game. First, that the game is simple. It means that coalitions either win or lose. Okay, the value can only be 0 or 1. And the second assumption is that the game is super additive. Okay, super additive means that the value, if you add together, if you union 2 disjoint coalitions, then together they make at least as much. Okay, and simple super additive games have a property that is easy to verify, that every 2 winning coalitions must intersect. Okay, because they can't make more than 1. They can make 2 together because there's no 2. There's only 0 and 1. Okay, so every 2 winning coalitions intersect. So suppose we have these 2 winning coalitions. We know they intersect somewhere. For example, in 5 belongs to both of them. Every coalition induces some subtree in the tree. This is a tree decomposition of the game. So the red coalition is contained in the red subtree, and the blue coalition is contained in the blue subtree. Okay. And we know that since every 2 winning coalitions intersect, then every 2 winning subtrees must also intersect. And so now we can add another winning coalition. It also has a winning subtree, which say a green subtree, which will intersect the red one and will also intersect the blue one. So there will be some point where all of them intersect, right? Because if you have a set of intersecting subtrees that are pairwise intersecting, they have to be all intersecting somewhere. Okay, just check that. It's an easy fact. Okay, so we know that there's some node of this graph where all of these subtrees intersect. Okay, say some node Z. Okay, so all winning subtrees contain Z. And this means that all winning coalitions intersect Z. So I don't know that all winning coalitions intersect. This might not be true, but all winning coalitions intersect Z. Okay? I mean, every winning coalition has some member from Z. So now the solution is easy. Okay? We just pay 1 to every agent in Z. Okay? We know this is stable because every winning coalition contains some agent from Z. Okay? So it gets paid at least 1. Okay? And we pay at most the tree width plus 1 because the tree width is defined like the maximum size minus 1. Okay? So now we just need to extend it to general games. Yeah, this completes the proof. For tightness, I will not show, well, I'll just show you the drawing of the example because it's really cool. I did not make this drawing. Yair, my co-author, did. It's just, so there's a graph. The graph is the heavy edges. And we use these Fano planes to somehow define the winning coalitions. Yeah, it's a nice construction, but it's a bit contrived. So it might be the case that a lot of games have actually better bounds if you show that something happens, that you know something about your graph, not just the tree width. Okay. Okay, so this ends the technical part. I'll spend like the next 5 minutes just discussing some implications of this result. And I hope that maybe you can help me think of more, or if you have more questions. So first of all, the cost of stability is a design tool, right? If you're the center and you want to decide how much to invest or how to stabilize a project, then you can use this bounds on the cost of stability as some design tool to better understand how you should allocate funds. But it's not just that, and this relates to, I think, what Bo asked earlier. It's also an inherent measure of the instability of the game. So I mentioned, I think I mentioned the least score. This is, suppose that you don't have subsidy, and instead the coalitions or the members of the coalition are willing to somehow lower the requirement. So it turns out that there are like tight technical connections between these two notions, and if a game is easy to stabilize, it is also inherently more stable. So the members do not need to lower their requirements much. Okay, so this means that this structure gives you some handle on the inherent stability of the game, or how easy it is to achieve cooperation, not just by subsidy, but in any way. Just means that the game is more stable. Okay, that's one thing. Second thing. Okay, so you can say, yeah, but where does this Myerson graph come from? Right? So a lot of games have been studied in the cooperative game literature, and they did not mention the Myerson graph, but they used some graph in the construction of the game, in the definition of the value function of the game. Okay, so these papers, they don't cite Myerson. I don't know if they even knew about Myerson, but it turns out that you can take their graph, the graph that they use in the definition of the game, and just use it as if it was the Myerson network. So even though they defined it for other terms, just as an auxiliary to define the utility function, you can actually say, just take this graph, whatever graph you used, and use this as the interaction graph, and results will hold. And so there are other games defined on graphs where this does not hold, but in most of them, in all these classes, we can use that. And in fact, it goes both there. So we can do the same on hypergraphs. So hypergraphs also have tree width. It's defined roughly in the same way. And these are special classes, but these classes, in fact, cover every game. So every game can be defined using these models. And if the game you define happens to be defined using a low tree width network or low tree width hypergraph, then you already know that you can bound its instability. Okay. Okay, now a word about complexity. So we know that a lot of problems are just in cooperative game theory are computationally hard. This is maybe not surprising because in a naive approach, just writing the game down requires 2 to the power of n numbers. And it's maybe not surprising that if you have some succinct representations of a game, then still computing the core or computing other things can be difficult. And in many cases, it is difficult. Even, for example, computing the optimal coalition structure can be difficult in many cases. And this is arguable, what I say here, that it's an AI measure, because there are other people who are interested in that for different reasons. But at least within AI, it is mainly used in the analysis of algorithms, of the efficiency or runtime of algorithms. So a natural question here is, okay, so suppose we have this Myerson graph, and we know that there's a low tree width. So can we answer some of these questions? Like, can we compute the core allocations faster? Can we find the optimal coalition structure faster? And this is a natural question, and it turns out that no, you can't. Okay, so even if the tree width is 2, so you can't compute core allocations fast, and in the general case, and you can't find the optimal coalition structure fast. So it's kind of weird. So bounding the tree width of the Myerson interaction network, it does not help you in any computational way, like it's supposed to. On the other hand, it gives you some other property that has nothing to do with computation. Okay, it gives you a bound on some economic or game theoretic property of the game. Okay, and it's only just one thing remains to ask. So how can we actually use that, or what else is there left to do? So can we somehow leverage this observation that the tree width can be also useful for other things, not just for computation, in other games? I don't know, maybe we can lower price of anarchy type of results in various games on graphs and things like that. Find any other uses for tree width, or maybe other graph measures. Okay, that would be one question. And another question links back to the motivation that I gave at the beginning. So if we want to apply this for real cases, okay, then think about a power grid or a water irrigation network. There's a physical network, and it is somehow related to the social structure. Okay, so maybe you can only form a coalition if you're along the same power line, but maybe it doesn't necessarily have to be the same constraint. So these are somehow related, but it's not the same. And you might need like finer notions. So maybe it's not just possible and impossible. Maybe some coalitions are somehow more likely to form, okay, and others are harder. So you don't need to think a lot about them. So I think this is a promising direction, and developing the theory in that direction can also enable to put it back in the real world and maybe making the core useful again. And yeah, that's it. So.
We have a little time for questions.
So, is there any hope of understanding a regime where the cost of stability is close to 1, like 1 plus epsilon? I mean, if you're thinking of the sort of subsidy motivation,
Yeah.
it's a little hard to imagine the government investing as much in a subsidy as the entire value of that, that
Yeah.
part of the
It's a great question. It seems that the tree width alone is not sufficient for that. You'll need something more intricate. And I guess that the graph structure alone would also not suffice. So you'll have to somehow use the properties of the game and the properties of the graph. And this question is particularly important, I think, if you look about cost-sharing games. So in most real applications, what we're actually sharing is not value, is cost. And then it's not clear what the graph structure says and if you can still use it. So that's another direction that I did not mention. So develop the symmetric theory for cost allocation games. And there, of course, the subsidy cannot be more than the full value, because the worst, like not the worst case. The worst case for the government, everybody are free eaters, right? And yeah, that's a good question.
There is also this counter effect in that
No, it would still be the most stable. So if you look like on the least score, for example, then still the most stable least score would be for the welfare optimizing coalition structure.
Right, but I mean, it's difficult because we don't really, it's hard to predict what happens when the core is empty, I suppose, but yes, if we said that people play the least core,
Yeah.
what do we know about the relationship between the welfare and the welfare maximizing core and the welfare maximizing least core? Do we know anything about that comparison?
It basically like bounds on the least score. Yeah, so there's some literature on that.
That is the subsidized and then subsidy where you make the pie bigger and then the player by themselves make the pie and it's also bigger.
Yeah, but like a somewhat related question is, suppose that for some reason the government wants to subsidize a particular structure that is not maximizing the social welfare but maybe maximizing some other thing, then you can still do that. You can condition your subsidy on a particular structure being formed, right? Yeah, so that's one thing.
Yeah, I wonder if there are cases where you can, like, if you can manipulate the structure within a combination within an organization, minimize the, I mean, do you see?
Yeah, so that's a great design application, right? So you can think, okay, instead of throwing in more subsidy, let's remove these 3 edges somehow. You know, let's tweak the graph. Let's, I know, fire this employee. So there are examples where you can lower the true width by removing very few. It's usually a difficult, like computationally hard question.
So if you,
but
what if
yeah.
you add edges, does that always?
Yeah. So yeah, in this under this definition, more edges is less stability because it allows for more coalitions to be formed, right?
I've seen that actually in source code repositories. Like, there's this question of how do you divide up so that we decide to share a repository that we're doing lots of things, and later on there's merge costs. But the way to actually get things reasonably stable is to make it very hierarchical, basically a tree.
Oh, I see. Oh, that's interesting.
Yeah, so the Mangesh is like from political science, and she took it to the direction why hierarchical, social structures are more stable and so on. But I think that this shows that it's not really the hierarchy; it's just the structure. Because it doesn't matter who's the boss. Even if it's a graph, you can take any node to be the boss.
But that, like, just like the ice cream bully, is a question of can you make this formalism different such that you are considering what each person is getting, right?
Okay, so you say, can you subsidize a more fair solution?
Yeah.
Okay, so yeah, that's a good question. So there are actually 2 types of solution concepts in cooperative games. So I glorified the core, but the other important solution concept is known as the Shapley value. And Shapley value has nothing to do with stability. It's just looking for what would be a fair solution. But we can actually think about these things together. So suppose that you like the Shapley value or some other fairness inspired solution concept. You can say, I want to stabilize that. So I want to throw in enough subsidy so that the Shapley value will be in the core of the new game. Okay? And it's a well-defined question. I don't know the answer. So for example, that in convex games, the Shapley value is already in the core. The core is non-empty, and the Shapley value is in the core. So maybe it means that maybe you don't need to work very hard in order to subsidize the Shapley value. We have a conjecture, basically, that there's another point solution concept, which is called the nucleolus or pre-nucleolus. And our conjecture is that the pre-nucleolus is the allocation that is easiest to stabilize. Yeah, we don't know if it's true, but it's a nice open question. Yeah.
So I want to ask a question, a follow-up question about what Alan said about reducing the cost versus stability by removing edges from the graph. I don't know if you take this into consideration. There may be a value that an edge is bringing, to the game
So you say that it matters which edges you remove because it might affect the value, and this is true, right?
Yeah.
So if you look about it, so we did not like formally consider this design problem of how to remove edges, but if you are going to do that, yes, that it's something you should take into account. You might remove like the wrong edges, and you manage to, so you can remove all edges, right? Then you achieve stability, right? But of course you destroyed like most of the value. So yes, it's a good question. I don't have a good answer for that, but I mean there are lots of open questions that come out of this like single answer maybe. I think it's good that it raises more questions.
Okay, thank you, Reshef.
Thank you.